A warm welcome to my garage workshop. I have got this old Colchester lathe. We started dating about 25 years ago, and our toothbrushes have been in the same mug for 5 years now. I absolutely love this lathe, but it became time to spice up our relationship with this CNC attachment. In my system, the longitudinal movement is achieved by motorizing the compound slide, and the stepper motor driven cross slide snaps to the tool post. The X-axis motor is plugged to the controller unit, then power and the spindle tacho sensor by another connector. I bet that back in the day when this lathe was built, they couldn't see this coming. Ouch! At the first glance it seems like this thing can only do straight lines, but we'll soon find out that the old hound can learn new tricks. The motions are controlled by Mach 3 motion controller. The dimensional accuracy comes from the 0 backslash ball screw. The tool paths are from Fusion 360. This cold roll mild steel usually gives quite crappy surface finishing, but even with this cheapest possible carbide insert, the result is pretty decent. Even the magician himself is surprised. I used to have this CNC converted mill and lathe combination, but I had to get rid of it to make room for beefier CNC mill. Like any mini lathe, it was good in two things: being small in size and cutting light stuff like antimateria and thin air. But machining a metal stock was usually objected loudly. Having a full-size CNC lathe is rarely justified in a hobby workshop, and very clumsy as only lathe. With this setup, I can turn larger objects than in a regular mini lathe. The 100 by 100 mm travels allows me to cut football-size radii. And no, even if I screwed up badly with my coordinates, the 4" by 4" travels aren't just enough to cut imperial football-size radii. Nor that I want it. Let's take a look how the attachment was made, and you will see some aspects about the design. First thing was adding timing belt teeth for the compound slide knob. The keyway was shaped in the lathe by an improvised tool. And no, my lathe is not broken. I will later show you the origin of that weird noise. The Colchester engineers designed the dial so that it shoots the steel balls and springs in 3 directions around the shop floor. First when disassemble, and several times in reassembly attempts. This plastic tool came in handy. The teeth could have been cut to the original knob too, but I wanted to preserve it in case this attachment fails. Here my newest employee, the Bridgeport Interact 1, is milling the next part. Like all my machinery, this too is old enough to drive a car, buy liquor and have its own children. This one isn't a drinker. But in a weird sense it's giving birth to my little CNC attachment. Then it took some manual milling maneuvers. This tilt feature helps Lathe with the timing belt. I took the original heatsinks from the stepper drivers and mounted them directly to the base. Two CNC parts later, I was able to take the first smoke out of the thing. The 2-3's USB breakout board was chosen by small size and low price. Then I started assembling the electronic stuff to the sheet metal casing. First was the jog wheel. Adding cherry on top. The arcade joystick wasn't in my original plans, but became a must-have item once I spotted it in the electronics equipment store. It made the switch arrangement a bit too crowded. It takes less than a minute to throw the central unit on top of the compound slide. There are no other modifications on the lathe but the knob. And the pulley teeth actually gives nice grip on manual use. And it looks like the knurls belong there. The central unit can be used independently as a power feed when turning tapers and chamfers. Unfortunately, there's no backslash adjustment in the Colchester compound slide acme nut, but I will correct this injustice later. And again, the surface quality is from some other universe compared to manual cranking. And like most of my designs, the cross-slide plans were defined by the raw stocks I found in my scrap metal bin. For some reason I decided to use manual milling and push the envelope on material removal. And it looks like I managed to remove the temper out of the drawing. Checking that I'm in the right furlong. The correct fit sideways for the carriage blocks is important because they have ridiculously small M3 mounting screw holes. Let's waste few moments of our lives to study my cross-slide design. Usually these guides are assembled so that the rail is stationary, just like the railroads are fixed to the planet. and the carriage is the moving part. This leads to all kinds of problems, like very long overhang for the tool holder. This is more pronounced with internal tools. Unlike trains, linear guide slides don't mind being the stationary part, and the rails can move all they want. Now the tool holder can be used with less overhang for both internal and external tools. I think. Next part to be made is the tool post. I tried the senior YouTuber's karate whack to divide the billet, but almost lost a finger in the process. So I used my bandsaw with better success. The slots for tool shanks were machined to both sides of the tool post. I didn't feel like power snap my tap, so I used a simple tapping guide here. The slide plate was first skimmed with my DIY fly cutter. Then the roughing cuts were made. And the tool post was TIG welded to the side plate. The final cuts for the guide rails were made after the welding to avoid effects of thermal deformation. Just the fit I was aiming for. Like the guide carriages, the rails have mounting holes for M3 screws. Those tiny screws can't hold very much cutting forces, so I thought it would be a good idea to fix them with a snug fit to the body. I didn't feel like power snap my tap, so I used my fancy tapping guide here. Next item to be made is the housing for the angular contact bearings. Here you can see the source of the weird sound in the keyway cutting scene. This is my prototype for a precision feeding dial for the Apron hand wheel. Where the original hand wheel gives very rough 25 mm per revolution travel, the 3D printed dial goes 2.5 times faster and gives 10 mm per revolution feeding. With this dial I hit the desired positions every time. I have some plans to make the new version of this apparatus simpler and quieter. Maybe I will share this project with you later. But now back to the bearing housing. It jumped back and forth between all my machine tools. But just after the bearing housing was finished, the ball screws and the bearings arrived. Usually these are assembled as a pair against each other, and I thought it would be a clever idea to be able to adjust the preload axially. But I had made a mistake here. The bearings I had ordered already had 2 rows of balls and a factory preload. I just lost the ability to adjust the preload, but now I have a spare part if any backslash occurs in the future. So I machined away the portion for the other bearing and gained a little bit of extra travel for the cross slide. Small screws were added for retaining the remaining bearing into the housing. Then I made the housings for the ball screw spindles. They were bought to tight size together with the mounting plate. A 3-point micrometer is the best tool for measuring the deep bore. Now the rails are assembled to the slide plate, and the ball screw spindle nuts in their housings. The other spindle nut housing has a slot for backslash preload adjustment. Just like two nuts can be adjusted together in a bolt by rotating them against each other. The spindle nuts came with a transport dummy tube to hold the balls in their aisles before the screw is mounted, and is pushed away by the screw. Same thing with the other spindle. The linear carriages have pieces of rails for the same purpose, to hold their balls before the final assembly. The fixed spindle nut was first tightened, and then the adjustable spindle mounting screws were put loosely in their places. The backslash adjustment was made by feeling the resistance in the rotation caused by the preload. Then the mounting screws tightened to the final torque. Then a spacer to replace the mistake bearing. And finally the two parts can be married together. And everything is running smoothly. Then the stepper motor was brought in, and the coupling was tightened. Then I made rectangular heads for 8mm screws. The screws can now be used with an Allen key or the original Colchester T-wrench. Now the new crosslight can be placed into a regular tool holder. The structure became incredibly sturdy. My doubt about the Runtish linear guides was somewhat inflated. The CNC tool post accepts now both external and internal tooling. The tool height is adjusted in the original quick change tool post. There's a link in the description for the CAD model of the assembly. Please take it more like a reference or for inspiration, not as a building instruction if you decide to make your own. I had big ambitions to show you some CNC threading, but I was unable to get the spindle speed sensor working with the Mach 3. Even the index pulses seems to be right. Maybe there's some issue with my settings, or the breakout board doesn't support this function. But let's now take a look about some of the stuff I have been able to pull through. You could easily think that this is a ram pipe for my son's moped, but you couldn't be more wrong. Changing any performance parts to a street moped is highly illegal in this part of the world. In my years I have learned that not all brown things are necessarily chocolate, but this traditional Finnish Easter egg is, and actually very good too. At the end, I would like to emphasize the importance of maintenance of your machinery. Or just enjoy my human privileges granted by Isaac Asimov's second law of robotics.